Saddleback College Robotics is proud to present our 8th generation rover, Agamemnon. Our team has continued to both improve and develop entirely new systems to optimize our approach for the 2026 University Rover Challenge missions.
This year, our mechanical team focused on redesigning subsystems that underperformed during prior competitions, and we continue to make iterative improvements on other systems. We've opted to keep our field-tested and reliable welded aluminum chassis. After experiencing issues with ground clearance and traction at comp, we spent months prototyping several wheel designs, resulting in a new 3D printed TPU tire that's 50% wider and 38% larger in diameter, with a negligible increase in weight. With an additional 3 inches of ground clearance and improved tread design to handle Mars-like terrain, our new wheels have enabled us to climb stairs for the first time in our team's history.
We've continued testing and refining our 6-degree freedom robotic arm, equipped with all custom harmonic and cycloidal gearboxes, allowing it to lift over 5 kilograms. We've also been hard at work designing a new arm from scratch, exchanging 6 degrees of freedom for 4 rotational axes and 1 custom linear rail. Our new arm makes use of compact BLDC servos with integrated drivers and encoders, using several belt transmissions to remove 3 of 5 motors off the arm entirely, with our wrist differential moving the remaining 2 motors closer to the fulcrum. While our arm is still undergoing extensive testing and development, we're confident it'll be ready by URC.
The development of a custom reconnaissance quadcopter has begun. Key motors, propellers, controllers, 12S lithium-ion batteries, and a lightweight carbon fiber molded frame will allow for flight times of 30-plus minutes.
Agamemnon's electrical system has been expanded and redesigned with a focus on enhanced arc precision and advanced scientific instrumentation for accurate data capture. The robotic arm incorporates magnetic Hall effect sensors to enable position-independent startup and improved inverse kinematics performance. The arm's power architecture was overhauled with a custom power distribution board providing real-time monitoring of current, voltage, and temperature for improved reliability and fault detection.
This year, we have made significant advances with our inverse kinematic system. While autonomous stiping is still in development, operators at the base station can view a 3D model of the arm's current pose alongside our new graphical user interface built in Foxglove, which allows for configuration and startup of the rover and presents telemetry data. Control of the rover remains split between 2 independent operators with separate gamepads for granular control of the arm and drive subsystems. Rover control and digital camera feeds are facilitated by a 2.4 GHz point-to-point link, while 2 1.2 GHz links provide analog video streams. Operators can provide GNSS coordinates through the base station, to which the rover can navigate and perform a search action on arrival. Real-time kinematic positioning allows centimeter-level accuracy with regards to the rover's position. Recognition of water bottles, mallets, and ice picks is facilitated by a new custom-trained YOLO model. Meanwhile, our obstacle avoidance system utilizes 2-dimensional LiDAR point cloud data to navigate around obstructions.
Our new science payload has been optimized for reliability, with redesigned soil cache geometry, improved lid linkages, and a new mixing system to more thoroughly suspend material in solution. Our drilling platform lowers to the ground, where server-powered lids are selectively opened to collect material only at required depths of 10 centimeters. Excavated material from each site is directed to a different cache to prevent cross-contamination. Peristaltic pump motors deposit an assay buffer to each cache, where motorized stir rods thoroughly suspend ATP in solution, which is then pumped to our new analysis system. This light-sealed 3D printed chamber houses both our PMT and a custom linear actuator that moves samples from different sites to the sensor, detecting trace amounts of ATP.
Our science mission is dedicated to the detection of extant life in subsurface soil samples, with updated procedures for chemical luminescence analysis of adenosine triphosphate. Sites of interest will be selected based on various habitability criteria derived from Mastcam-identified geological signatures. Samples collected and reserved for further analysis will be exposed to enzyme catalysts and substrate reagents in the analysis chamber. The produced luminescence reaction from ATP will be measured via the photomultiplier tube, and the reaction data will be transferred wirelessly back to the base station. Additionally, our package includes a probe designed to measure in situ temperature and moisture levels.
Last year, we learned that our biggest limiting factor is not the rover's capability, it's operator experience. For that reason, this is the first year that Saddleback Robotics has had a dedicated testing team. Our focus has been on replicating URC missions to stress test both the rover and its operators while identifying key reliability concerns and areas for improvement. We have been conducting mock mission and performing off-site field testing to evaluate performance under realistic conditions. In the remaining months before competition, our priority is maintaining a rigorous tri-weekly training schedule to ensure our operators perform consistently and confidently under pressure.
Saddleback Robotics thanks you for your consideration, and we will see you in Utah.